So the appendix is on the fundamental theorem of algebra. So as a dessert, you will take home the knowledge of why this famous theorem is true, not just that it is true. And I'll put it between quotation marks, the so-called fundamental theorem of algebra. Okay? As you know, the theorem says the following. Let's say that f of z, I shall write it down explicitly, cd and zd plus cd minus 1, zd minus 1, and so on, to c1 z plus c0 is a complex polynomial. Of degree d, which is greater than or equal to 1. Often people forget to state this hypothesis. When I stated, for example, a minute ago, I forgot to mention it. Because a degree 0 polynomial is a constant. For example, take the constant 2. Well, this constant polynomial 2 doesn't have a root anywhere. You see? So the fundamental theorem algebra works only when the degree is greater than or equal to 1. Okay. And the theorem is that there exists some complex number such that f of z is 0, as you know. Proof. I shall draw a large picture here. Let's say that this is the origin. And take a point z, and let's go around the circle once. Okay? So assume for a contradiction I'll show you the picture in a moment. That for all z, f of z is non-zero. Okay. Now, this proof depends on the following fact, which I shall first discuss intuitively. Thank you very much. Look at this point and consider a loop which does this. It's not quite circular. How many times did I go around this loop? Did I go around this point? Once. Let's say that we count it as +1 if I went around in the anti-clockwise, counterclockwise direction. Okay? How many times did I go around? -1 time. Okay? How many times did I go around? +2. Now, a tricky one. How many times did I go around? -1. That's good. Okay. Here is a really tricky one. How many times did I go around? I passed this through this point. Well, it's not clear, right? Because let's compare this with two other scenarios. Suppose that I go like this. How many times did I go around? I went around like this. -1. But let's do like this. You see? It's +1 in this case. So that's +1, that's -1. How do we count this? There's a discontinuity, as you can see, as I move this picture a little bit. Are you with me? We cannot, in fact, define how many times we went around in this case. If you pass through the point, you lose track of the count. Anyway, you cannot define sensibly a rotation number, how many times you went around, in a continuous way. Is that okay? Good. So please bear that in mind. And let's come back to the proof of the fundamental theorem of algebra. So let's assume that there is no zero. There is no root. Now, as the point Z, which we shall write in the polar form as r times e to I theta, revolves around the origin 0 once, which is what we do, and we are saying that this radius is r. Okay? Let us look at what does z to d. Z to d is r to d times e to I d theta. You can think of the case when d equals 2, for example. When z goes around the origin once, what does z square do? This is the radius rd. What does z square do? It starts from here, and then, don't you know? Look at e to I theta. It becomes e to I d theta. You are going around with d times the angular speed at the distance r to d. So if d is 2, what happens? When z goes around once, what does d square do? It goes around twice. That's correct. So you get a picture like this. Goes around, and while z is going around once, its image, you should imagine a movie, goes around. In fact, it's going around along the same trajectory, but in order to show you that it's going around twice, I'm drawing them slightly differently, but in reality, it's exactly the same curve that it's tracing twice. And then it comes back, and then returns to the initial point. Okay, it goes around twice. So this is what, for example, if z is here, maybe z squared will be somewhere here. This is not a very good picture, so z squared. Okay? It goes around twice. So in the general, d times around the origin, and f of z, well, it's a complex number, right? So I don't know what it does, but anyway, it's going to go around the origin a number of times. Okay? I don't know what f of z does while z goes around once. It goes somewhere, goes on a hike up the Muizenberg mountain, and then comes back, and then goes back to bed, and then, comes to class, and who knows? I mean, it goes. But when z completes the turn, f of z returns to where it started. Okay, so it draws a curve, which closes up a loop, so it goes around the origin a certain number of times. So revolves a certain number, which we shall call nr, because it depends on r. You see, if r is different, maybe f is going to be different. But it doesn't depend on theta, because I'm going around once anyway. So a certain number, n sub r times around the origin. Okay. However, this is where we are going to get the contradiction, so please be careful. We were assuming that f of z is always non-zero. In particular, when f of z goes on a hike and comes back to class and goes to bed and so on, and it goes back to where it started to complete a loop, this curve, this loop, never goes through the origin. Okay? Therefore, we can count this number, n. If it went through the origin, as we saw, this number cannot be counted. It would be impossible to define this number continuously. Is that okay? So because of this hypothesis that it's everywhere non-vanishing, this nr is well defined. That's the expression in mathematics. So there is no problem defining this number, whereas if f vanished, became 0 somewhere, you cannot define this number, so the proof stops there. You cannot say it revolves a certain number of times because we cannot define this number. But as it is, because we are assuming that f of z is everywhere non-zero, we can continue the proof. Logic does not stop. Okay, so it's well defined because precisely by assumption. f of z never passes through 0, correct? Okay. Well, now we are ready to hit the main part. Let's look at the case r equals 0, and then start increasing r more and more. We are deforming the picture, and we'll see that there's a contradiction. When r equals 0, well, z reduces to a single point, right? So f of z, which is f of 0, so I don't know where f of 0 is. Maybe it's somewhere here, or somewhere here, somewhere here. In fact, f of 0 is going to be c of 0, whatever it is, okay? So f of 0 reduces to a single point. So let me write it a bit more in a more civilized way. So f of 0 reduces to a single point, which is f of 0. Yeah, f of z actually reduces to a single point, f of 0. So naturally, what's the n of 0? How many times did f go around the origin? Well, if I stay there, how many times do I go around the origin? 0 times. So this is 0. Okay? On the other hand, if r is very large, this is my notation for very large. Okay. Well, what is f of z then, when z is very large? In that expression, we wrote, this is the highest order term, and all the others are lower order terms. So if z is huge, this term is going to dominate, and the others will be insignificant. One way to see it, if you are a little nervous, is to write this as cd zd, and you factor it. And then you get 1 plus c of d minus 1 over z, plus c of d minus 2 over z squared, and so on, right? And if z is huge, all of these will be very small. So this will be approximately equal to 1. So indeed, this dominates. Is that okay? So in this case, f of z is approximately cd times zd. You don't have to worry about cd. So this one, you see, goes around the origin. How many times? It's essentially zd. How many times do I go around the origin? D times. So this is d. And remember that this d is greater than or equal to 1. But look, the number of times I go around the origin is a continuous function of the loop that we are taking. Right? If I modify the loop a little bit, it's still the same number of times we go through the origin. So n sub r depends continuously on r, and it cannot jump from 0 to d because d is greater than or equal to 1. Depends, sorry. So it's a, is an integer depending continuously on r. Yes. The principle we are using here is a very famous principle. You know all about continuous function. You can kind of imagine the graph of continuous function. Please imagine that you have a continuous function, but whose values are all integers. What can you say about this function? Constant. Can you see that? A continuous function, which takes values only among integers. It must be constant. Because if it's not constant, that means that here it takes some value, here it takes some value, but this value is an integer, this value is an integer, and it cannot do this because it has to take integer values everywhere, so the only option is for it to jump from here to here, which is not continuous. Okay? So constant functions that are continuous, integer valued functions that are continuous must be constant. And so it cannot jump from 0 to d. Yeah? As r varies. But we seem to have observed that it jumped from 0 to d when r is 0, n of 0 is 0, when, so this is, excuse me, r is very large, n of r is d. What happened? Something went wrong. It's a contradiction. And the contradiction came from that offending assumption that there is, that offending assumption that there is no root to the polynomial. Because we made that assumption, this n could be well defined. Logic took us through this step, and we are forced to conclude by the deformation argument that this cannot happen. Okay, a contradiction. Establishing the fundamental theorem of algebra. Well, I hope you can take it home and enjoy. Good. Let us then finish. As I said, tomorrow I'll give you a quick review of everything that we did and then show you something entertaining. But just to finish, you know, when we started the course 3 weeks ago, on the 6th of January, was it? It feels like a long time ago. But it's so short. Do you remember the first problem that we discussed? We discussed the square or the disk. And can you connect those 2 points and this point and this point and this point and this point with continuous curves so that they don't intersect and so on? You remember this? And we saw it was a cute problem, Poyer's problem, that by deforming the picture you could solve, and by deforming back you got the solution. Let me give you another puzzle. Huh? And I want you to work on it for maybe 5 or 10 minutes. And then we'll take a break. Well, then I'll give you a solution and we take a break. All right? Let's consider the following picture. I'm going to draw the picture in a certain order so as to make a beautiful picture. Let's have a rectangle, yellow rectangle, whose sides are A and B. Okay? So inside a rectangle of sides AB, inscribe an ellipse. You know what that means? I draw an ellipse which touches the rectangle on all sides. There exists a unique ellipse like this. You can always do this, and there's only one. Inscribe an ellipse. And if you work quite hard, you can write down the equations of this ellipse, and so on. Okay? And then inside the ellipse, inscribe another rectangle. So here, the first rectangle was drawn in yellow, and the second rectangle will be drawn in red or pink. Which is similar to the original rectangle. I hope the meaning is clear. So here, I could draw lots and lots of rectangles inscribed. For example, I could draw a rectangle like this, I could draw a rectangle like this, but please draw a smaller rectangle which is similar to the outside rectangle. In other words, the ratio of this side to this side is always A to B. Is that okay? Question. What is the ratio of areas of the big rectangle to the small rectangle? So what's the area of the big one compared with the area of the small one. What is this? Please work together and try to solve it. Go on, go on. I'll give you the solution in about 7 minutes. Have you started doing some calculation?
Square first.
You try to do it to the square first, okay. Have you made progress? Is everyone suffering? Good. Okay, everyone is suffering. Because my purpose is not to make everyone suffer, you might have the impression that it is, but in fact it isn't. Because my purpose is not to make everyone suffer, but to teach something interesting to everyone, let's stop. We know, suppose that our life depended on it. Suppose that if we cannot find this ratio of areas correctly, Ames releases a lion which will eat me up. Then I will certainly calculate, right? I can maybe say that, okay, those are the axes. I can calculate the equation of this ellipse, and then I can find out where those 4 corners are, yes? And then I can multiply and so forth, yes? But as it happens, Barry Green is a very, very good director and will not release a lion on me. So let's think one last time topologically. What happened to you? Okay. Do I have any yellow left? What happened to my yellow chalk? It would be nice. I must have. I know that the yellow chalk exists because I use it. Ah, here it is. Thank you very much, Xavier. First, we shall say that, well, this problem looks difficult, so we are going to deform the problem. Okay? This is the original problem. And we want the area of yellow, big thing, over the area of the small rectangle. Okay. This side is A, this side is B. But let's squeeze this side until this side also becomes B. Or equivalently, let's stretch this side so that this side also becomes A, okay? So this picture can be deformed to the following picture. Where both sides are A, in other words, it's a square and a circle with another sort of square inscribed in the middle. In the course of this deformation, the ratio of areas does not change. Is that okay? Because I'm just scaling one direction by some factor. Is that okay? So the area of this big square over the area of this small square is exactly the same as the previous area. So this area, if you like, the ratio of areas is invariant under this deformation. Now, what is the ratio of areas between the large and small? Well, still it looks difficult. Yes? True. Still it looks difficult. So I'm going to deform the problem again. Please watch what I'm going to do. This is the large box. I have a circle inscribed in it. Excuse me. Okay. Circle like this. And I'm going to take this middle red square and rotate it by 90 degrees. Huh? And I have this square. Okay? And if you want, you can think of those lines cutting. When I do this, of course, the area of the outer yellow box divided by the area of the middle, now 90 degrees rotated by small box, this ratio is of course the same as the previous ratio, yes? But look, What's the ratio? Look at this. That's a triangle, and that's a box. Do you see the ratio? It's equal to, what is it? 2.